A plus R, A plus B goes to R, and R plus B goes to S. 1, 2. We call this an example of series parallel reactions. And we started, we call them series parallel. Why do we call them series parallel?
Because we can look at, with respect to B, it's a series reaction, I believe.
Are you guessing? Or
With respect to B is parallel?
with respect to B is parallel. So again, right here, B goes to R in the presence of A, and B goes to S in the presence of R. And in the presence of A, it's
a series reaction.
it's like right here, A goes to R in the presence of B, and R goes to S in the presence of B. So it looks serial with respect to A and parallel with respect to B. We've studied each of those individually, and now we're trying to study them together. And we said this was a typical circumstance where this type of reaction comes up is to look at your notes.
I am.
Not now, you're supposed to look at them before you come to class.
No, I don't know.
You obviously are not interested in passing.
I am.
You're not interested in this class at all. If you were interested, you would look at your notes.
Polymerization?
Polymerization is one example. Okay. So we decided to look at selectivity, and we wrote out phi of R of A, presuming that we're interested in some intermediate length polymer. And we saw that we could write this as RR over minus RA, where RR was equal to what?
Minus, no. It's K1 CA CB minus K2 CR CB.
Good. And this is, of course, we're assuming constant density. And
K1CACB.
K1 CACB. And what we can see immediately is that CB cancels out, so the concentration of CB does not affect the product distribution here. And you can see that because B sort of is necessary for both reactions equally. Having more B doesn't favor one reaction over the other, because it's CB to the first power in either one. And this just gives me 1 minus K2 over K1, CR over CA. And when I assume constant density, I set this equal to dCr minus dCA. From here over, there's no constant density assumption. The constant density assumption is when I set it equal to this, dCr dA, because in the constant density assumption, RR is dCr dt and RA is dCA dt. Okay, then we rearrange this and we integrate it, and we got this expression here. You can notice this is in a different handwriting. Okay? It is something we derived last time. I just want to manipulate it into a form in your textbook. So let's do a little manipulation, and I'll look at the form of the textbook. So one thing I could do is I can move this to the other side of the equation. I can do that easily just by changing that to an equal and a plus. No, I'm sorry. What was this before now? This was equal, right? Yeah. So I can just change it to a plus. That's moving that to the other side of the equation. And I can divide by CA, by the coefficient here, and by CA of 0. So I would like to have CR of t of tau divided by CA 0, or CA of 0. And that's equal to CR of 0 over CA of 0, this thing, times, now I divided by this, so I have this thing divided by this thing, which is just CA of tau over CA of 0 to the K2 over K1. So I change the sign on this to flip them. I have this term. And what else do I have? Now I also have 1 over 1 minus K2 over K1 times. Okay, so I've divided by this. So I've got, so this has got two factors. This has got CA of tau, and it's got CA of tau to the minus K2 over K1. When I divide by this, then that thing cancels out. And I have CA of tau, and the other thing I have here is over CA of 0, because I've divided by CA of 0 and this thing. So that's the first term. And the second term is I'm dividing by 1 CA of 0, and that cancels the 1. And then I have CA of 0 to minus K2 over K1, and I'm dividing by this thing. So again, I'm going to flip those. So I've got CA of tau over CA of 0 to the K2 over K1. And let's see how close that is to the form we're trying to get. Okay, so I've got, what are we? It just seems to be a minus sign is the only problem. Okay, there only seems to be a problem with the minus sign here. So this should be a minus. So somewhere along the way we lost the minus sign. So it may have already been in this particular equation. So I'm going to let you find it. But otherwise we got all the factors right. So this was a plus just now, so I'm going to choose the minus sign here to get like this, and then we have the right answer. So you have to find the missing minus sign. And it may have already been missing over here. Okay, so here we have CA of tau over CA of 0. CR of tau over CR. CR of tau over CA of 0. So remember, we're interested in how much of the intermediate we can get, and here's an expression for that. Is there anything we can see from looking at this expression? Okay, this is the effect of the, if you like, the inlet. So if I have R in the inlet, I have this term. If I have no R in the inlet, this term is gone because CR of 0 is 0. And the other term, what can we say? Well, one thing we can see is that if K2, the sign changes depending on whether K2 is bigger than K1 or K2 is smaller than K1. So you can see there's a big difference between the situation K2 bigger than K1 and K2 smaller than K1.
So when we say CR or not, do you mean for the first reaction itself? Initially,
What, I'm sorry?
the CR not?
CR of 0 is CR of tau is equal to 0. So it's CR that's going into the reactor. It's concentration. So that's something that you usually have some control over. So if there may or may not be R going into the reactor, because here are my reactions. If I only have A and B going in, the CR is going to 0. On the other hand, if the reaction mixture is coming out of some other piece of equipment, there may be some R in there. So allowing both possibilities. But again, what you can see here is that that the sign is going to change here depending on whether K2 is bigger than K1 or K2 is smaller than K1. On the other hand, that's somewhat compensated by this. If K2, let's say K2 is smaller than K1. Remember, this had always better be positive or non-negative. We don't want any negative concentrations. So clearly if K2 is less than K1, then this is a positive number. And if K2 is less than K1, then this thing is raised to a power less than 1. Now, of course, Ca is a reactant. So if Ca is a reactant, then Ca of tau is smaller than Ca of 0. So this is a number less than 1 raised to a power less than 1. So it gets bigger. So this is bigger than that, and everything's positive. On the other hand, if K2 is greater than K1, then this is negative. If K2 is greater than K1, then this is a positive power. If this is a positive power, and this is less than 1, then this, when I raise to positive power, it gets smaller. So this becomes less than this. So therefore, again, this is negative, everything's positive. So we're safe. Okay, now let's say I wanted to calculate CS. I could go through and write out the equation for CS, but we also had our conservation principles. If you remember, we have our reaction vectors. What were my reaction vectors? Who was that to? Did you ask me that? Did I ask you that? Did I ask you that?
Minus 1, 1.
0.
0.
And the other reaction vector?
0, -1, -1, 1.
0, -1.
1.
And our perpendicular vectors, we said one of them we could carry over just from A goes to R goes to S, was 1, 1, 1, 0. And what was the other one? The other action vector? It's in your notes. 0, 1, 1, 2. Okay, so this told me that that CA plus CR plus CB plus, no, CA plus, in fact, this isn't right. This was, if I do this A, B, R, S,
1, 0.
then this is 0 minus 1. No.
No, it's not 1, 1, 0. It's 1, 0, 1, 1. For
Okay,
the
this is, let's say this is minus 1, minus 1, 1,
0.
0.
It's the
And
other.
this was 0, minus 1, minus 1, 1. So here I had, this is not 1, 1, 1, 0. This was 1 for the A, 1 for the R, 1 for the S. And this was for the B, 1, 1, 2. Is this correct? Okay. So we had CA plus CR plus CS is equal to CA of 0 plus CR of 0 plus CS of 0. And from the second one, we had CB of 0, CB of tau plus CR of tau plus 2CS of tau is equal to CA of 0 plus CB of 0 plus 2CS of 0. So if we know the inlet conditions, the right-hand side, and we know CA and CR, we can calculate CS from here. And if we know, just from this expression, this gives us CS. And if we know CS and CR, we can calculate CB from here. So there's no need doing lots of algebra here. As long as we know CA, and CA just decays in a certain manner, and CR, then we're okay.
Just for the second equation, on the right-hand side, shouldn't it be CB of 0 plus CR of 0?
Yes, yes. CB plus CR. Okay, so that's the result for the selectivity for a plug flow reactor. And let's do the same thing for ACSTR. This was for a plug. So for a plug flow reactor, we write out, well, what happens for a plug flow reactor? So a plug flow reactor, we can start with the taus. So we have tau, we know, is equal to C in minus C out over minus R out. From what we handed down the sheet, to make sure that's correct. Yeah, C in minus C out over minus R out. And I can write this for R and for A. This is true for any species, so I write it for R. So it's CR in minus CR out over minus R out. And minus R out is just the negative of this. This is plus RR. So it's K2 CR out, CB out, minus K1 CA out, CB out. And I can also write this for CA. So it's CA in minus CA out over K1 CA CB out. Or if I manipulate this to get it in the following form, this thing divided by this thing. So if I write it as CR in minus CR out, in is of 0, out is of tau, divided by the negative of this thing. So I've got CA of tau minus CA of 0. That's equal to K1 CA of tau, CB of tau, minus K2 CR of tau, CB of tau, over K1 CA of tau, CB of tau. And what you can see here is, even though I started from the design equation, I manipulated it into a form where the right-hand side looks just like the right-hand side here, except these were as a function of tau a variable, and here tau is fixed at the end of the reactor. So whereas this varies with position in a plug flow reactor, this is a fixed case because the CSTR is stirred. And the difference also is on the left-hand side, instead of having a derivative, I have just the deltas. So this equation is exactly parallel to this equation. And what you can again notice, for the exact same reasons, the CB's cancel out. And I just have to manipulate this into a form. Remember, what I'm interested in here is CR of tau. I'm interested in getting CR of tau. So where do I find CR of tau? I find it here and here. So I have to multiply through by the denominators and try to solve for CR of tau. So I multiply this times this, and I get K1 CA. When I write no tau, when I write CA, I'm going to mean CA of tau. Otherwise, I'm going to write CA of 0. CR of 0 minus K1 CA CR. Same thing with CR. If there's no argument, I'm going to mean as a function of tau. And that's equal to K1 CA squared plus minus K1 CA CA of 0. Times this. Minus K2 CR CA plus K2 CR CA of 0. So all I've done is I've multiplied out the denominators. And now let's get the CRs on one side of the equation and solve for them. So I can move this to the other side of the equation. I have K2 minus K1 CACR is equal to K1 CA squared minus K1 CA CA of 0 plus K2 CR CA of 0 minus K1 CA CR of 0. And now I divide both sides by K2 minus K1 CA. And let's see what I get. Okay, and I guess to make things also a little easier, so I'm going to divide numerator and denominator by K1. And probably because I want to have a 1 minus K2 over K1, is that what I want to have? No, that's okay. There it is. Okay, and let's see what I get. So, CA, and I'm probably going to want a CA 0 down here. So I'm going to divide by CA of 0. So let's see what I'm left with. I'm left with CR over CA of 0. And let's see, are there any terms that look alike up here? Actually, I have a CR here, that doesn't look right. So this term survived, this term survived, this term, okay, this probably isn't right. No, it is right. Okay, so I'm not doing the algebra right. So there's a CR in 3 of these terms. So I didn't do the algebra correctly. I should have isolated 3 terms on the left. Let's do it again. not 2. So I've got CRs in all these terms. Okay, so in order to do that, I'm going to bring this to that side of the equation. So I've got a K2 CA of 0, CA. K2, no, I'm sorry. K2 CA of 0 minus CA times CR. K2 CA of 0, sorry, CR, K2 CA CR. So those two terms. And then I have this term. So I have a plus a K1 CA. All that times CR. And that's equal to everything else. So that's got a K1 CA CR of 0 plus K1 CA times CA of 0 minus CA. And that's these terms. Okay, so now I'm going to divide by the coefficient of CR. What K is this? K1. CA. And I'm also going to divide by CA of 0. And let's see what sort of form I'm trying to do. So notice over here I can factor out the K1 CA from both of these terms. So I can put the CR of 0 in here. And this CA of 0 I can put here. And do I want to have K2 over K1? Yeah. So I'm going to divide top and bottom by K1. And let's see what I'm left with. I'm left with CR of tau over CA of 0 is equal to, the K1's canceled here. So I've got CA over CA of 0 times CR of 0 plus CA of 0 minus CA divided by CA plus K2 over K1 CA of 0 minus CA. Let's just see if that's right before I start analyzing. Yeah, that looks correct. Okay. Let's see what I can notice here. One thing you can notice is that CR of 0 plus CA of 0, from this balance here, CR of 0 plus CA of 0 is the total concentration minus CS of 0 going in. Well, of these three. Or if you like, it's CA plus CR plus CS minus CS of 0. That's not a big deal. Okay, what else can we say about this? Again, we want to make sure it's the right sign. Well, that's no problem here. Everything's positive because CA is always smaller than CA of 0. So both the numerator and the denominator have those differences, and they're both positive. And let's see if there's anything else we can say here. At tau is equal to 0, what happens at tau is equal to 0? At the beginning of the reactor, I should just be left with the initial condition. So when tau is 0, this is 1. This is the same as this. So that's 0. These two are the same. So this is 0. So all I have is CR of 0. When tau is 0, I have CA of 0 here. So I just get it again. So at least that works out. Let's make sure that works out here as well. When tau is 0, well, when tau is 0, this is 1, and this is 1 raised to the power. 1 minus 1 is 0. So this term drops out. This just becomes 1, and I'm just left with CR of 0 over CA of 0. So they both work out at tau is equal to 0. And what we should see here, let's see if we can see it analytically, is that the CRs, at least the term non-involving CR0, let's see if that goes through, if we can see if it goes through maximum. So let's see if that's at all obvious from these equations. Okay, yeah. Let's see what we can do here. So we noted if we ignore the CR0 term, then what we said is that at tau is equal to 0, this is 0 and this is 0. And this is just CA of 0. So, let's see. Yeah, this just becomes 1. Right. I'm sorry, it doesn't even matter. When CR of 0 is 0, then when tau is 0, this is just 0, the numerator is 0. The denominator is not 0 because this is 0, but this is not 0. So, and tau is equal to 0, the part without the CR of 0 is 0. What happens as tau goes to infinity? As tau goes to infinity, CA goes to 0. So this becomes 0, this becomes 0, this becomes 0, this becomes 0, but I still have the CA zeros. So what we see is that at tau is equal to 0, the term without the CR0 is 0, and at tau is equal to infinity, it's 0. And in between, it's non-negative, so it has to go through a maximum. We should be able to see the same thing here. Again, if we ignore this term, if we look at this term, we noted that at tau is equal to 0, this whole thing is 0. And at tau goes to infinity, CA of tau is 0. CA of infinity is 0. So it's again, it's 0 at 0, 0 at infinity, and otherwise it's non-negative. So therefore it has to go through a maximum. Now, of course, whether the whole function goes through a maximum or not depends on CR of 0. It could, because the CR of 0 is not just standing alone, it's divided by the denominator. Question? Go ahead.
You said that C equals 0, right?
Tau equals 0.
At tau equals 0, CA is CA 0. So what if you're at an initial condition that's away from the maximum? So then you wouldn't have, you wouldn't go to a maximum even if you.
That's what I was saying. The maximum, whether you get a maximum in CR, it depends on CR of 0. If CR of 0 was 0, the rest of the equation would go through a maximum. The way you see whether the CR goes to a maximum, it depends on where CR of 0 is. And if you remember when we, in the simple case, when we were looking before, and A goes to R goes to S, and we were plotting A, R, and S, we said if you start, you're not looking, so there's no point in explaining. Yeah. If we start with CR of 0 over here, then we're not going to have a maximum going to the right. If we start to the left of here, we will have a maximum. So it really depends on CR of 0, whether you have a maximum or not. You can see that here. If CR of 0 is 0, or small enough, then we will have a maximum. If CR of 0 is too big, we won't have a maximum. Any other questions? Okay, so, question? All right, so what sort of general conclusions can we draw here? Generally, the plug flow reactor, if I have reactions in series, we know that the plug flow reactor does a better job for the intermediate, as long as I choose tau correctly. Now, what happens, and as we saw, this type of reaction, the series parallel reaction, is a reasonable model for polymerization type reactions. And we've started to get some insight into the polymerization reactions. And even and now of course, in order to compare in series parallel reactions whether the plug in the series is better, I would have to plot this expression relative to this expression. So I believe they plotted in their textbook, and they find again that the plug flow reactor gives you a higher CR max than the CS0 if you plot these. It's not obvious when you look at them. It's very hard to compare them because here I have powers and there I don't have powers. So without actually doing a plot, it's very hard to see. But typically, the plug flow reactor does better. Now, I did want to make a couple of comments about biological reactions. There are two generic types of biological reactions. One of them is a fermentation reaction. Fermentation type reaction. And the other one is a microbial reaction. So a fermentation reaction would be, for example, an enzyme-driven reaction. So if you have an enzyme-driven reaction. So for example, if you want to make wine, that's typically a fermentation type reaction. On the other hand, a microbial reaction involves microbes. So here an example is wine. Microbial reaction, I have a microbe, like a bacterium. And a typical reaction, example of that, is say making yogurt. What's the difference between making wine and making yogurt, other than the fact that you get different products?
Are the other ways different?
I'm sorry?
The rates will be different?
Tell me how.
Because with an enzyme, it's an enzyme will bind a substrate to the product where it's bacteria. I feel like it would be exponential.
That's not getting to the point I'm looking for.
For the yogurt, the product plays the role of the catalyzer.
Okay, the difference is in the yogurt, the bacterial reaction, when you not only produce yogurt, you also produce more bacteria. And the bacteria are the agent, the catalyst of the reaction. Whereas in an enzymatic reaction, a perfect enzymatic reaction, the total amount of enzyme is always constant. Some of it's being occupied by binding to substrates, some of it's unoccupied, but the total amount doesn't change. There's a big difference there. So what happens in a microbial reaction, so typically we usually use Michaelis-Menten kinetics here. I gave you a homework problem on Michaelis-Menten kinetics. Michaelis-Menten kinetics, the key step in Michaelis-Menten kinetics is to realize that the total amount of enzyme, concentration of enzyme plus the concentration of bound enzyme bound to substrate, is a constant. On the other hand, in a microbial reaction, because the product acts as, one of the products acts as a catalyst, this is autocatalytic. So Michaelis-Menten kinetics, if I plotted the rate versus concentration of substrate, then it goes up and then it levels off. Because at some point, above a certain concentration of substrate, all the enzyme is busy. All the enzyme is used up. So putting more substrate in doesn't accelerate the reaction. This is no free enzyme. Whereas in a microbial reaction, we know that the more, well, if I plot the rate, say, versus, well, what was I plotting it against? Well, if you remember when I plotted the rate versus tau, the rate versus time, then we found a curve that looks something like this. or the rate versus conversion of substrate. If I applied the rate versus conversion of substrate, initially I had very little. It also looks something like this. That is, when I have lots of substrate, when the substrate isn't converted, I have very little bacteria. I start out with very little bacteria, so the rate is slow. At the end of the reaction, I've used up all the substrate, so there's not much reaction. But in the middle, I've got lots of substrate and lots of reaction. So now if I plot versus, if I replot this as the rate versus the concentration of substrate, you have to keep in mind exactly what I'm talking about here. Again, the curve will look like this because when the conversion of substrate is high, the concentration is low. So this corresponds to here, and this corresponds to there. You have to remember exactly how I'm doing this. This is under the situation where at high C substrate, I have low C concentration of bacteria, and vice versa. So under these conditions, I get this curve. Because what I'm thinking of is I'm thinking of a reactor, where I started out, either a tau is equal to 0 or a t is equal to 0, with lots of substrate and very little and very little bacteria, and then I let the bacteria's reproduction become autocatalytic. So notice, under these conditions, the curve looks like this, and it's very different. These are very different situations. In particular, this is monotonically increasing. It levels off, but it's non-decreasing, whereas this goes up and goes down. So when I have monotonically increasing rate functions, what is the type of reactor I always want to use? What was after? A plug flow reactor. For monotonic rate functions, I always want to use a plug flow reactor because a plug flow reactor always has, for any given conversion, it gives me the highest possible concentration, and the higher the concentration, the higher the rate. So I always want to have the highest rate, so that I have the most efficient reaction. On the other hand, that's not the case here. If I go to concentrations that are too high, then I have a slow rate. If I go to concentrations that are too low, I have a slow rate. It's non-monotonic. So if you remember, when I plot minus 1 over R versus C, or versus X, I get a curve that looks like this. And if I want to go from here to here, what did we say? What were the good strategies for this type of reactor, Okay, well, I don't know if it's exactly half, but partly plug and partly CSTR. So let's say this is the inlet. Should I do the CSTR first or the plug first?
CSTR first.
And at what outlet concentration of the CSTR? What outlet conversion?
Outlet would be
Where on the curve would the outlet be?
the minimum.
The minimum, right. So I would have a CSTR followed by a plug. And if I were stuck using only a single reactor, if I couldn't build 2 reactors, what type of reactor would do best here? No. A recycle reactor. So the best I would do, if I could only build a single reactor, would be a recycle reactor where I operated it at the optimal recycle ratio. Questions? Let's see how many showed up today. Okay, so are there any questions on selectivity? All right, well, up until this point, let's just review a little bit of what we've done this semester. Someone have a watch so I can see, I don't talk forever. 11:55. 11:55? I'm like 10:55.
Should I put it?
Yeah, I'll give it back to you. Look, you have an incentive, otherwise I'll just talk forever if you don't. Okay, if you remember, we started out the semester making lots of assumptions. Early in the semester, we started out by saying we're going to talk about single reactors. We also said we talk about single reactions. And our reactions would be isothermal.